scale similarity models. So the idea here is, if you recall the energy spectrum E of k is a wave number, okay. So in that, let us say you have a cutoff wave number, kc is the cutoff wave number, let us say. Cutoff wave number, as I said before, is that like you are resolving up to that particular eddy size. This wave number is of course representing a certain eddy, okay. Wave number is related to the wavelength of a particular eddy. So the anything from the origin to up to cutoff is the resolved part here. So this is the resolved part and this is the modeled part, okay. The SGS is supposed to model the last tail of this contribution, okay. So if you simply recollect this energy spectrum with a cutoff wave number and this, and then of course you have Kolmogorov length scales at this end, and you have your either energetic length scale or a pseudo length scale, whichever you want to use it to account for the other one. Here the idea is that the scale should be similar on either side of the cutoff wave number. That means the eddy which is just above or below this cutoff wave number should have similar behavior. So there should not be any abrupt change at the cutoff, right. So the Smagorinsky and other models, it models everything before the cutoff wave number, sorry, everything after the cutoff wave number and before it is resolved by the mesh. Here the idea came that the eddies or scales just below and above or just around this cutoff wave number has to be similar. That is the idea of scale similarity or scale similar, right. So in this type of model, so the model philosophy is scales just above and below the cutoff wave number Kc, okay, or similar, that is scales smaller than a scale smaller and larger than delta, can think of as this, right, since the cutoff wave number corresponds to your filter size or the grid size that you are capturing. So the eddies that are just smaller and larger of the delta, they should be similar, okay, or similar. Scales just above and below the cutoff wave number or smaller and larger than your delta or similar, and therefore the name came scale similar. So to do this, we go back to tau ij SGS, because every SGS model or in LES is about modeling or finding these 6 unknowns, subgrid scale stresses, tau ij SGS, and the exact form of this is ui uj filtered, which is the unknown, we do not have access to this, and you have ui filter, uj filter. This is the exact equation. Now what I can do is this ui further I can decompose, okay. So here ui itself is decomposed into the filter and its fluctuation, or not the fluctuation, the residue. Okay, so this is nothing but your filtered component, and this is the residue. So if I split this UI into these two components, I can rewrite this as I have UI filter plus residue, and then UJ filter plus its residue, filtering operation over it, minus UI filter UJ filter. So you can rewrite this as, now it is looking lot similar to this Reynolds decomposition, even though it is not. Right, we are simply splitting the instantaneous velocity into its filtered and residue. So now I have UI bar, UJ bar, okay, filtering on top of it, first component, and then I have the two components which have interaction between filtered and residue, which is UI bar, UJ filter, plus I have UI residue, UJ filtered, filtering on top of it, plus UI residue, UJ residue filtered, minus UI filtering, UJ filtering. Okay, so here I can rewrite this as tau ij SGS is equal to the first term and the last term minus UI UJ, and then the other two terms, which is where there is interaction between filtered and residue, plus UI, and the last term which is somewhat looking like a Reynold stress, so I have classified this into three types of terms. Is there any term that is exact here, or all terms requires modeling? The first term on the right hand side is exact, right? Exact means I can do this. I have UI bar access because that is what is being computed. I can do one more grid filtering operation on that. So this is exact for me here, right? So this is exact, as well as it is looking lot similar to the dynamic Leonard stresses at the grid filter level. So this is actually called Leonard stresses. Okay, so this is called Leonard stresses. Luckily it is exact, no modeling required, and these are called cross stress terms, cross stresses, because it is looking like there is a cross interaction between the filtered and the residue component here. This is, as I said, looking somewhat like a Reynolds stress, so we call it Reynolds SGS stresses. Okay, so we'll call this equation, let's say, let's call it star, some number. So among these three, one is exact, the other two requires modeling. If you do that, the tau ij SGS is closed and you can solve the LES calculation. Okay, so symbolically this is written as this tau ij SGS is written as Lij, Leonard stresses, plus Cij plus Rij. So this is exact, it means no modeling required. This is a big advantage over your Smagorinsky type of models, where all the SGS fluctuations are modeled. Here at least some part of the SGS fluctuation is exact here, the Lij component over Smagorinsky, right? The other two has to be modeled. These two has to be modeled. Okay. So now there are two main class of models here. One is called a Bardina model, the other one is a Speziale model. So that is for the way the Cij and Rij are modeled. So the first one is the Bardina model. So before that, you can say that, or let's talk about Bardina model. No issue. So Bardina model, okay, it's 1980. So the idea here is that you can say this Cij is the cross term, and we assume here that this is responsible for the interactions between the scale that is just above and below the cutoff number, because it has terms which is both residue and the filtered. Okay, so here it is assumed that Cij is responsible for cross interaction between the filtered and the residue scales. Okay. So in this model, what we do is Lij is computed. So the tau ij SGS you can get first by modeling Cij model. It is modeled as Cr, a model constant, followed by Ui filter, Uj filter minus Ui double filtered, Uj double filter. Remember, filtering again in LES in general is not same as the originally filtered quantity, right? For box filtering, exception is only the cutoff filter. And here the model constant Cr is set equal to 1.1 in Bardina model. And in Bardina model, the Rij is omitted. This is not modeled, and they found that there is an issue. What is the objective of an SGS model? To dissipate the energy that it is sent to SGS scales, right? And Bardina model was found that it is not dissipative enough. Some energy accumulation is occurring. So this Rij has to be modeled, and that is corrected in the Speziale model, right? So note that the main objective of an SGS model is to dissipate resolved fluctuations. The resolved energy, and that is not happening here, right? So in Bardina model, it was found that, or was found not sufficiently dissipative okay, because this Rij is omitted. So the next model by Speziale corrects that. The Speziale model by say 1985. So this model takes into account the Rij contribution also. So here the tau ij SGS is now Lij plus Cij plus Rij. right? Lij is exact, so nothing to be done, similar to the Bardina model. Here Cij model is similar to that, except that model constant is value is changed. In Cij model is set equal to same as Cr, Ui filter, Uj filter minus the double filtered velocities, but the Cr model constant is 1 instead of 1.1 in the Bardina model, and we will see why this gives an advantage later. Okay, and the Rij model term, here Smagorinsky idea is used here. Okay, similar to Smagorinsky, it is set equal to minus 2 Cs square delta square S Sij bar, that is like Smagorinsky. Right. Cs is your Smagorinsky constant. Again, user dependent here, even though it is not going, you are not going to define for all the SGS scales, because it is only some fraction of the total SGS scales contribution is you are going to have a user dependency here. The Cij and Lij are computed, only Rij you have some user dependent values going into this, right? So if I now substitute all this into tau ij, SGS is equal to the Lij, if you recollect, it is Ui filter, Uj filter, and then a filtering on the entire product minus Ui filtered, Uj filtered. Okay, that's the Lij. This is your Lij term. Now plus I have this Cij term in the Speziale model, which is Cr, which is 1, followed by Ui filtered, Uj filtered, minus Ui double filtering, Uj double filtering, and the finally the Rij term, which is minus 2 Cs square delta square. So now it's readily seen, by setting Cr equal to 1, this term is going away, less computations for you to do. Okay, this term is going away because this Cr is 1 here. Therefore, this tau ij SGS is now Ui bar Uj bar whole bar minus Ui double filtering, Uj double filtering, minus 2 Cs square delta square Sij filtering. This is the final form of your Speziale model. And if you look closely, what is this? This looks exactly similar to your dynamic Reynold stresses, only that the operation is done at the grid filter level. Right. So this is analogous to your Lij, that is dynamic Reynold stresses. So this gives another class of model for you, a scale similarity model, somewhat different from the Smagorinsky, and the advantage is that some fraction of the SGS fluctuations are computed exactly, the Lij component, and Cij is also computed. As you say, Cij also requires just filtering operation. There is no extra assumptions here, right? Only that Rij is the factor that is where some modeling component is going. Other than that, Lij, Cij is like what you can get by just one more filtering operation at the grid level.